could actually do both. Water could actually, in some cases, donate an H+. In some cases, it can accept an H+. So we call that amphoteric, when it can act as either an acid or a base. And then I think I wrapped it up here by talking about how, remember, so since you can do both, the amount of acid and base in water is always a constant, we said. It's always this, the Kw 1 to the negative 14th. So we said, okay, well, that means in water, if the acid goes up, the base must have gone down, and vice versa, right? Remember saying that? Hopefully ring a bell. Hope you did a little homework on that. So, but of course we don't just normally measure the amount of acid or base just purely as a concentration. Normally what we use is a scale called pH, which you've probably all heard of. The pH of, you know, the soil, the pH of your water, the pH of your deodorant, strong enough for a man, made for a woman, whatever, right? pH. So the pH scale is another way of trying to measure the amount of H+, the acid, the proton. So pH is literally, it is the negative log of the concentration, the molarity of the hydronium, or the acid. And remember again, H3O plus hydronium is the same as H+, right? Because H+ in water truly does actually combine to make hydronium, but you'll see it both ways. So pH is the negative log of the acid concentration, the H+, the hydronium concentration. Okay? Now, we're going to see there are several of these scales that start with P, like pH, and P pretty much always means the negative log of something. So the pH is the negative log of the H. We'll also see the POH, which is the negative log of the OH, and things like that. So on the pH scale, basically the way it works is, if anything less than 7, so 0 to 7, that pH means it is acidic. Of course, the lower it is, the more acidic it is. If the pH is greater than 7, so 7 up to 14 is our max, that means it's basic. And if it's exactly at 7, then we say it's neutral. So again, in water, we said in water, the concentration of hydronium was 1 times 10 to the negative 7th molar. So, if you were to try that on your calculator, try the negative log of 1 times 10 to the negative 7th, you're going to get 7. So when your acid concentration is the same as pure water, it's just neutral. There is no pH. If it has more acid than that, it's going to wind up being less than 7. It's going to be acid. And if it has less than that, well, it's going to wind up being basic. Because again, if the acid goes down, the base must go up, and vice versa. So let me spend a little time showing you here on the pH scale how to use that, how to use the log key. If I'm not a key you use a whole lot, but I just want to show you first. There's a little chart I like out of your book. It kind of told you what the pH value was of various things. So again, pure water, 7. So 7. So that's when the hydronium concentration is equal to water. It's 1 times 10 to the negative 7th molar. So if you get more acid, it begins to go just a little more acidic. So like milk is slightly more acidic than water, actually. Then urine, bread, potatoes, coffee, tomato juices, sodas, etc., etc. Now we're going to see here in a second that a change of 1 pH doesn't seem like much, but every change of 1 pH means it is 10 times more acidic. So a change of 7 to 6 means you have 10 times more acid than regular water. Change of 7 to 5 would be 10 times 10, 100 times more acidic. To 4 would be 10 times 10, 1,000 times more acidic. So think about this. A soda has 10,000 times more acid than regular water, because it went from pH 7 to 3, for example, right? So it's super acidic compared to regular water. So it's like, 7 to 3. That's not big. We'll change to 4. Well, that's really 10 to the 4th, 10,000 times more acid. We'll see, because we'll see the log scale is what's called a base 10 scale. So every change of a log is a base 10. So let me show you how we're going to do sig figs on this, because it's a little different, but it still follows all of our rules. So, let's just try some of these in our calculator first. So, try in your calculator, try to do the negative log of 1 exponent negative 4. So, find your log key. 1 exponent key negative 4, right? So that's one, and then hit the log key and then negative. So you should get 4 if you do it right. If you're not getting 4, let me know. I can try to help you out there. But so 1 exponent key negative 4, and then log and then negative again, right? To make it negative log of, right? Remind you here, pH is the negative log of the hydronium. So put in this hydronium concentration and see if you get 4. Are you using the exponent key, or are you trying to do times 10 to the something?
Times 10 to the something.
Why are you not using your exponent key? It's only been 14 weeks. Come on, exponent key. 1 exponent log and then negative. Oop,
Sorry.
yeah, it was there for a second. I saw the 4. Yeah, because times 10 to that's going to give you an extra 10. It's going to screw you up. Okay, so what does log do? Okay, again, as I said, the log scale is oftentimes called the base 10 log. Maybe heard that before in a math class. What a log literally does is it takes away the 10 to the. So the log just strips out the 10 to the. So if I take away the 10 to the, that leaves negative 4. Then if I do the negative of negative 4, I get 4. So that's all log does. But if it's not a nice even number like 1, well, it is going to make it slightly bigger or smaller than the exponent. So now how does sig figs work? Well, the log basically turns this exponent into a 4. So the log takes care of this first part. Where do the sig figs come in then? Well, the sig figs are whatever numbers are in front of the exponent. So if there's 1 in front of the exponent, there's going to be 1 decimal. If there's 2 sigs in front of the exponent, there's going to be 2 decimals, etc. So, let me try to illustrate this a little better. So this determined that 4, which means this one out here determines there's 1 sig fig here. Now try the next one. Try negative log of 8.0 exponent key 6 negative. And you should get 5.1. So make sure we get our calculators working here. Everybody get 5.1? Okay, so the log takes this 6, and that determines this is going to be around 6. But it's not 1 now. If it was exactly 1, it'd be exactly 6. But it's a little bit larger, so this winds up being a different number. So notice there are 2 sig figs here, so I'm going to have 2 decimal places here. So same thing on the next one. 2.4 to the negative 8th. Okay. The 10 to the determines the number here in front of the decimal. Since there's 2 decimals here, there's going to be, not 2 decimals, I'm sorry. Since there are 2 sig figs here, there's going to be 2 sig figs or 2 decimals here. Again, this is not really a sig fig because this came from that exponent. This is not really a sig fig because it came from that exponent. So 1 sig fig, 1 sig fig, 2 sig figs, 2 sig figs, 2 sig. Do you kind of see how that works? Kind of. Okay, so how about the next one? Did you get 7.62 to work? I just want to make sure we're getting that log key. Just to, again, just a key we don't use a whole lot probably. Everybody getting that? If you're not, speak now. I'm happy to show you how real quick. Or ask a neighbor. Okay. So let's just try a couple here. Let's try. So what is the pH of coffee? if the hydronium concentration is 1.0 times 10 to the negative fifth. This should be the easiest one ever. You don't even need your calculator. Because it's 1 times 10 to the negative fifth, so it must be what? 5. How many decimal places will it have, though? 2. There's 2 sig figs here. There's got to be 2 decimal places. Because again, the 2 to the negative fifth makes the 5. The 5 is not a sig fig, right? So if I do the pH of the negative log of 1.0 times 10 to the negative fifth, yes, the exponent up here will turn into this 5 out front here, right? It's these 2 here that tell me to put 2 decimals after it, so 0, 0. Again, this is not a sig fig. This came from the exponent. So 2 sig figs, 2 sig figs. Okay, try the next one. The hydronium of tomato juice. Yes, Maurice.
So the coefficient would tell you how many decimal places?
Yes.
Sig figs?
Exactly. Yeah, the number of sig figs here tells me how many decimal places or sig figs to put here. Because again, this is not really a sig fig because this did not have anything to do with precision. This just came from the exponent. Okay, try the next one. Tomato juice. Put it in your calculator and figure out how many decimal places it should have. Then ask your neighbor what they think. Okay, compare with your neighbor. What's the answer? What's the pH?
So does the whole exponent carrying over, does that only apply to one times? Because
I mean, it still carries over. I mean, that's what makes it 3 in this case. It won't be exactly 4 because now it's not 1, it's a little bigger, so it's going to make the number a little less than 4. But it still is determining that in a sense. I mean, if that was a negative 4, that wouldn't be 3 in front of it. If it was negative 3, it'd be 2 in front of it. If it was negative 5, it'd be 4 in front of it. If it was negative 6, it'd be 5 in front of it.
Okay.
So, did you talk it over? Did you agree? Agree on your decimal places and everything? Okay, so what'd you get? 3.674. Right. Absolutely. 3.674. Again, I have 3 sig figs here, so I'm going to put 3 decimal places here. Because this just comes basically from the exponent. Now, it's not 4 to 4 because it's not a 1 anymore, but it is still what makes that a 3. Okay, well, let's try this one. What I told you the hydroxide concentration was 1 times 10 to the negative 3, and I want to know the pH. So what would you have to do here? How could you find the pH? If I give you the hydroxide.
Subtract 14.
Yeah, that's one possible way. Yeah. Chrissy, what were you saying?
I thought it was the same way.
You mean do the negative log of the hydroxide? No, pH is negative log of hydronium. We have hydroxide. How do I find hydronium if I have hydroxide? We did this last time in class. What do we know about hydronium and hydroxide? What do we? Very last thing we did in class last time.
Is that like
Yes. We said the hydronium times the hydroxide always equals 1 times 10 to the negative 14th. That's called the KW. So if I know the hydroxide, I can find the hydronium. So the hydronium has to be 1.0 times 10 to the negative 14th divided by the hydroxide, right? Which was 1 times 10 to the negative 3rd. So 1.0 times 10 to the negative 11th. So now we can do the pH is the negative log of that. So what's that going to be? 1.0 times the negative 11th is going to give me what? 11.00. Right? Because again, we got 2 sig figs here, so these are our 2 sig figs here. 0, 0. Okay. Now I want to show you a few the other way, and then I'll talk about pH and what Reading said is also true with pH and pOH being 14. So what if I give you the pH and I want to know the hydronium? So let me show you how this works. Whoops, go back. So if the pH is the negative log of the hydronium, the hydronium must be, well, we have to move that negative over, make it negative pH, and then get rid of the log. We have to do what's called anti-log of both sides. And if you look above your log key on your calculator, it probably looks like 10 to the x. Because I told you, what does the log do? Well, the log goes in there and actually removes the 10 to the. So the anti-log puts back the 10 to the. So the anti-log giveth, and the log taketh away the 10 to the. So that is why that 10 to the is not an exponent key. Should be having an EE, right? So we're gonna do so. Move the negative over. It's going to be 10 to the anti-log of the negative pH. So, right, I move this over, and then I do anti-log of both sides. Anti-log is the same as 10 to the, so 10 to the negative pH. So let me show you how this will work. So on your calculator, let's try anti-log of negative 8.00 and see what you get. Should get like 1 times 10 to the negative 8th. But the question is it 1? Or is it 1.0? Or is it 1.00? Or what is it times 10 to the negative 8th? Definitely something times 10 to the negative 8th. So now I'm going to go backwards. Right, exactly. So I have 2 sig figs here. So I'm going to have 2 out here, so 1.0. Because again, this relates to this. Now we're doing it backwards. Now we're doing it backwards. Now we're doing it backwards. So this goes to this, so these 2 become these 2. Now we're doing it the other way. This becomes the exponent, so these 2 become the coefficient out front. Okay, try the next one. 3.7. Okay, let's say I was finding the pH and I give you this number. You would say, this becomes the 8, so these 2 become these 2. Now we're doing it the other way. So now we're going the other way. Now it's going to be negative 3.7, then anti-log, or however the calculator works, anti-log is negative 3.7. So it's going to be something times 10 to the negative fourth. How many digits should I have before it? Yes. How many decimal places did I have in pH? 1. So I ought to have 1 in the coefficient. So what times 10 to the negative fourth is it?
2.
Okay, we'll say it again. If I was going the other way, it would have totally made sense to you because I just showed you. Oh, this 4 becomes this. So I've got 1 here, so I got 1 decimal here. Now we're going the other way though. Do we just do that, right? If I'm doing it backwards, ignore this. If I just said, find the pH. Oh, you would have said, oh, 1 number, so 1 decimal. Now we're going the other way. So now 1 decimal becomes 1 number. We're just doing it the other way. Here it was 2 decimals becomes 2 numbers. Just doing it the opposite way. Just doing it the opposite. Okay, well, I'm going to skip the last one because we don't have a whole lot of time. I just want to show you a few little reactions here with some acids and metals. If we have time, we'll come back. So we've seen this before in lab where we have taken, for example, in class, magnesium metal. We did that like, was it 2 weeks ago with the gas laws? And you dissolved it in acid and it bubbled and made hydrogen gas. Remember doing that? In the big long tube. The big long tube called the eudiometer. So this is a very common kind of reaction between acids and metals. So you notice what happens, for example, is the potassium reacts with the nitrate to make potassium nitrate. And then the hydrogen is left behind. So hydrogen by itself is always diatomic, H2. So what kind of a reaction is this? Is this combination, decomposition, single replacement, double replacement? What is this? This is a single replacement because one thing is moving. The nitrate went from the hydrogen to the potassium. How about the next one? Magnesium with nitric acid. Well, the nitrate goes over here and makes magnesium nitrate. And that leaves hydrogen by itself. So hydrogen by itself is now H2. So that's a very common reaction where acids can dissolve lots of metals. Like I said, we saw this one in lab 2 weeks ago, right? So you had some magnesium. Remember that? You put it on a little tube. You had the HCl on the bottom of the tube. You put in the food color, and then you inverted it, and it came down and dissolved the magnesium and made gas. That was this one. Although our acid was HCl, but same deal. So in that case, it was HCl, so the Cl went over here and made magnesium chloride and hydrogen. Still the same basic pattern. So yes, that's a single replacement like we've seen before. All right, I'm going to pause for give you 3 seconds to finish your writing, whatever you're writing. Okay, now with carbonates and bicarbonates, it's a little bit different with acids. So this is, remember in the past we knew how to use solubility rules to tell if something was going to be aqueous or a solid. We're not going to be able to figure out something is going to be a gas. So here's our first gas we now know how to predict, hydrogen gas. Next one has to do with these carbonates and bicarbonates. So let me show you what happens here. Let's peek ahead real quick here. Okay. So look at 2HCl with calcium carbonate. This is written goofy. I don't know why I wrote it this way. Okay. Let me just write a reaction. Let me hide part of this for a second here. I'm going to write a reaction. Put down that first sentence. I'm going to hide this reaction and show you a different one. It might make a little more sense. So yes, acids react with carbonates and bicarbonates to produce carbon dioxide gas, water, and some kind of ionic compound. That part's true. But I just want to show you, break it down a little more step by step for you. Okay, so let's look here. So let's say I took HCl plus calcium carbonate Okay, now I'm going to have a double replacement reaction. So we could predict what's going to happen. I've got hydrogen with chloride and calcium with carbonate. So I'm going to swap and put the hydrogen with the carbonate and the calcium with the chloride, right? That makes sense? The same as any other reaction we've done before. So hydrogen with carbonate, what would that make? What's the charge on hydrogen? What's the charge on hydrogen? +1. Actually 1 plus, but what's the charge on carbonate?
2 minus.
2 minus. So yes, 1 plus, they would have to make H2CO3. Right? That would be the first one. And calcium with chloride, what would that formula be? What's calcium's charge? 2 plus. What's chloride's charge? 1 minus. So what would calcium chloride be? CaCl2. Good. And that corner solubility rules is aqueous. So let's balance this real quick. How would I balance it? Right, 2 hydrochloric acids. Okay, so here's the little thing that is unique. H2CO3, that's called carbonic acid. But carbonic acid is really just carbon dioxide gas dissolved into water. So whenever I see this stuff right here, I'm going to just break it up into what it really is, which is carbon dioxide gas and water. That's really what that is. And you see, if I put H2O with CO2, I would get H2CO3. So, whenever you're doing a double replacement reaction, and you get H2CO3, we're just going to erase it, mark it out, whatever, and say, aha, we're going to replace it with what it really is. CO2 plus H2O. So this reaction would really be 2HCl plus CaCO3 goes to CO2 plus H2O plus CaCO2. That's what I would really be writing. So again, I could literally just go back. Oh, let's just erase all this right here. It's really this. Are you with me? That's what it really is. Okay. Let's try another one. Let's try, what was the other one I had on here? Okay. HCl and sodium bicarbonate. Same thing. Okay. Let's try it. Let's prove it. NaCl plus sodium bicarbonate. I'm sorry, not NaCl. What am I saying? HCl. Thank you. HCl. That makes more sense. Okay, so let's do the same thing. You know double replacement reactions. You know how to swap the anions and make new products. So it was H plus with Cl minus and Na plus with HCO3 minus. Now we're going to put the H plus with the HCO3 and the Na with the Cl. So what are H and HCO3 going to make? H2CO3 again. And then they're going to have the sodium with the chloride, which is going to make what? What? NaCl, right? And this one's already balanced, I think. So I go, oh, aha, ding, ding, ding. Whenever I see H2CO3, I'm going to mark it out or erase it or something. And oh, no, it's not really that. That's really carbon dioxide gas plus H2O liquid. Are you with me? Just gonna erase it, scratch it out, whatever, and put what it really is. Okay, so I told you earlier, like I said, based on solubility rules, we knew how to predict something was a solid or an aqueous. Now we can predict if something is a liquid or a gas because we have liquids and gases now. So whenever you see H2CO3 as a product, just erase it or mark it out, whatever, and replace it with what it really is. Now let's say the equation came out balanced and I had two H2CO3s. Well, then I would have two carbon dioxides and two waters. If I had, right, because two of these would make two of these. If I had three of these, I would have three of these or whatever. Okay, so let's just try a couple reactions here. Let's just try this one. Zinc plus hydrochloric acid. So, this is just a single replacement. So here, what moves over? The hydrogen or the chloride moves over here with the zinc? Of course, because the zinc is going to become positive, so it can't combine with the positive hydrogen. So the chloride's going to move over. So I'm going to make zinc chloride. What would zinc chloride's formula be? Zinc's 2 plus, chloride is 1 minus, so yes, ZnCl2. And you hopefully remember your solubility rules. All chlorides are soluble except for silver, lead 2, and mercury, so soluble. So the chloride moved over. That left hydrogen by itself. Remember, hydrogen is all by itself, not in a compound. It's one of the 7 diatomics, so it's H2, and that is a gas. So there's a gas you know how to predict. Bubble, 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 bubble. Bubble's nothing, right? Okay, and I already bounced out, but the 2 are going to be HCl. Okay? How about this one? Let's try this one together. How'd you name that first one, by the way? Name that one on the left. How would I name this? Magnesium bicarbonate, or you could call it magnesium hydrogen carbonate. Either way, right? Okay. And how do you name that acid? Have a little practice. How do you name that acid? HCl. Hydrochloric. Okay, let's break it down. You're a little slow on that. Cl by itself will be chloride. Ide tells you hydroic. So chloride, hydrochloric acid. Okay, now let's do our little switcheroo. Swap the chloride and the bicarbonate. So magnesium goes with chloride, so that winds up making, what's magnesium chloride? MgCl2, good. Aqueous, solid, gas, liquid. Aqueous, because all chlorides are aqueous except for those 3 exceptions. Now I'm going to put the hydrogen with the bicarbonate. What will that make? Right, it makes H2CO3, which we know, aha, ding, ding, ding. I'm going to erase that or scratch it out or whatever and say, oh, that's really carbon dioxide gas with H2O liquid. Oh, I'm sorry. It was balanced. Yeah, there's a 2 there. Yes, but good point though. As far as balancing goes, it's always easier to balance it here and then break it apart. Yeah, balance it here and then break it apart. Very good point. Okay, your turn. Try this one. Sodium carbonate. And how do we name this one? Name this acid. What is this called? Nitrate. What do you do with 8? 8 goes to... 8 goes to... 8 goes to us. 8 go to just ick. So nitrate becomes nitric acid. Ide goes to hydroic. 8 goes to ick. No hydro. and ice goes to us. Only 3 rules. Okay, so try it out. So swap the carbonate and the nitrate. Swap those, give them new partners. I'm going to peek something on the PowerPoint while you're doing that real quick. Make sure I'm doing time for... Okay, good. Okay, well, let's compare with your neighbor whenever you get an answer there. See if you agree on the products. Excuse me. Okay, so we're going to put sodium was with carbonate, so now sodium goes with nitrate. So what's sodium nitrate? NaNO3. Solid or aqueous? How do you know it's aqueous? Anything with sodium, anything with nitrate. All the time, no exceptions. And now hydrogen was with nitrates, now hydrogen's going to be with carbonate. So hydrogen carbonate, that's what we're going to make that carbonic acid, which we now know needs to go bye-bye. So I'm going to scratch it out. But first, I'm going to balance it first. Let's balance it. How'd you balance it? 2 of these. Okay, now I'm going to go. See ya. It's really a carbon dioxide gas and H2O liquid. Okay. Now let's say, for example, the problem asks you then to take this molecular equation, give you the ionic equation. Well, remember you break up anything that's aqueous. So I would break these up into H plus and nitrate, this up into sodium and nitrate, but don't break up solids. You also don't break up gases or liquids or anything else. Okay, so that's one kind of an acid reaction. We have like an acid with something else. Well, how about just what's called a straight-up neutralization reaction, where you have an acid reacting with a base. Acid and a base. And anytime an acid and a base react, you always get 2 things. You always get some kind of a salt or an ionic compound and water. So acid plus base always gives a salt and water. Acid and base always gives salt and water. Here again, it's basically just a double replacement reaction. Pause for a second to show you. So basically what happened, well, we swapped the chloride and the hydroxide. So the chloride goes over here with the sodium, makes sodium chloride. The hydroxide goes over here with the hydrogen. And I mentioned before that water is basically the same as hydrogen with the hydroxide. So that's what I did. I just moved the hydroxide over. Boop. Oh, made water. Moved the chloride over. Made sodium chloride. So it's just a double replacement reaction. So if you think of water as HOH, it kind of makes it a little easier to see how that kind of happens there. Okay? Now, if we're let's say that we're going to do the netionic equation. Well, break up anything that's aqueous. Break it apart. So HCl makes H and Cl. NaOH makes Na and OH. NaCl makes Na and Cl. Water, liquid. So leave it together. If I cancel everything out, what's really happening in any acid-base reaction is the acid, the H plus, and the hydroxide, the OH minus, are making water. That's really all that's happening. Every pH reaction basically boils down to the H and the OH are making water. Everything else is just spectator ions. So all the sodiums and the chlorides and the nitrates, they're all just spectators. Okay, so just kind of keep that in mind. So every acid-base reaction is basically just acid, H plus, base, hydroxide, and making water. Pretty much everything boils down to that. Okay. Okay, so let's try to write a couple of equations here, and we'll see that pretty much anytime you have an acid and a base, we're going to get some kind of salt, ionic compound, and water. So let's try this one. Potassium hydroxide, and let's practice naming this. Let's name this acid. So what's that called by itself? Fate. 8 goes to what? Ick. So the acid must be sulfuric acid, right? Put the back for sulfur, not sulfate, sulfuric. So potassium hydroxide and sulfuric acid. So just do our switcheroo like always. Swap our hydroxide and our sulfate. Give them new partners. So what would potassium with sulfate make? What's the charge on sulfate?
-2.
2 negative. So what is it?
K2SO4.
K2SO4. Aqueous, solid, gas, liquid. What is it? Aqueous. How do you know? Anything with K, always soluble. And most sulfates too. Okay. What else do I make? H2O. Hydrogen with hydroxide is basically, right? I'm basically making hydrogen with hydroxide. Or H2O. And that, of course, is liquid. But again, it's a little easier to balance, as I mentioned way back with balancing, way back. When you're balancing, if you see hydrogen, hydroxide, and water, it's easier to think of that water as HOH. So 1 hydroxide, 2 hydrogens, 1 hydrogen. So we're going to do a little balancing here. So I'm going to put a 2 over here with my waters. And then I'm going to put a 2 over here with this. So 2 potassium hydroxides plus sulfuric acid makes potassium sulfate and 2 waters. Okay, try the next one. Try B. Excuse me. Good. What do you think? Swap your partners. So the hydrogen and the chloride, the aluminum and the hydroxide, they swap. So now the hydrogen goes with the hydroxide. That's just water. Or again, you can think of it as hydrogen with hydroxide if you want. That helps. And then aluminum with chloride, which makes what? What's aluminum chloride?
CO3.
Turn that around. AlCO3. Yep, always the cation first. Good. Solid, aqueous, gas, liquid. Aqueous, because all chlorides are aqueous except for those 3 exceptions. So now how would I balance this?
Put a 3 in front of the HCl.
3 HCl, okay. And 3 H2Os, absolutely, yes. Because notice I've gotten 3 hydrogens and 3 hydroxides. That makes 3 waters, hydrogens and hydroxides. Again, if you think of the water like hydrogen with hydroxide, it makes it easier to balance. Okay. Oops. Try the last one. This is a fun one. Oh man, but we need to speed up actually, so make it quick. barium with phosphate. Barium's 2 plus, phosphate's 3 minus. So what's barium phosphate's formula? Ba3, parenthesis, PO4, parenthesis 2. Aqueous or solid? Solid. And then H and OH, of course, makes water, which is liquid. Or again, for balancing purposes, if you want to think about it as HOH, that helps. So, 1 barium, 3 bariums. Let's make a 3 barium there. 1 phosphate, 2 phosphates. Put a 2 there. So I need 6 waters. Is that what you got? Something like that. Okay. Okay. Well. Now, there's a very kind of important technique we do in lab. We don't do it this semester, not this lab, but come back, we do it a lot in like 110, 111 and such, and it's called a titration. This is not the same as what's written as on titration in nursing, where they're talking about they're trying to titrate a drug to get a certain effect. Kind of similar, but this is a pure and acid-based titration. So in this sense, what we're doing is we're going to take either the acid or base, one of those we're going to know the concentration of, and we're going to use that to find the concentration of the other one. So for example, maybe you know the concentration of the acid, so you use it to find the base concentration, or vice versa. I know the base concentration, so I'm going to find the acid concentration. So now what's going to happen is you're going to basically add one or the other. You're going to add the base to the acid or add the acid to the base until we reach what's called the equivalence point. And the equivalence point is literally it's where the acid is equal to the base. So the titration goes up to that point where the amount of acid you've added or base added, whatever it is stoichiometrically equal to the amount of the other one that was present. That's called the equivalence point. And this allows me to figure out the concentration. I'll show you how in a second here. Pardon me. Okay. Now typically the way we tell this is we're going to use what's called an indicator. And an indicator is something that literally, its job then is to indicate when have I reached this equivalence point. And it changes color. The one we use a lot of times is what's called phenolphthalein. Phenolphthalein is a very common indicator. And it will change color from clear to pink as soon as it hits basically pH 7, neutral. Now actually it's when you're 1 drop past, but close enough. So, in the lab what you can do is you can have an acid, you can add a base to it, it stays clear, it stays clear, it stays clear, it stays clear. Boom, it turns pink. The second it turns pink, you know the amount of acid I added is exactly equivalent to the amount of base. So you can stop. So let me show you how I would use that in order to find these concentrations. So let's say I have an acid down here. So these are little H pluses down here, okay? So these are all little H pluses. And then I'm adding into it hydroxide. So what I want to know is, the way it would work is I would know the concentration of the hydroxide. I would know that's 1 molar or 2 molar or whatever it is. This one I don't know. Well, what I'm going to do is I'm going to add this in until when the amount of base I've added is exactly equal to the amount of acid that's present. That's when it's going to suddenly magically change color. So let's say each little molecule is a mole of H+. So if I have 5 moles of H+, it'll turn color when I've added what? 5 moles of hydroxide, because at that point, all the acid has been neutralized by the hydroxide to make water. So I do that, so I add a couple in, make a couple waters, and then when I add 5 in, boom, turns color, I know, it was that is what's called the equivalence point. So, oh, I added 5 moles of base. That means there must have been 5 moles of acid in here. Now I can find the concentration, because concentration is moles over volume. Oh, 5 moles of acid divided by whatever the volume of the acid was will give me the molarity. So let me show you that in the calculation here. So let's say we just did that. Let's say we took 10 milliliters of acetic acid. I don't know what the concentration is. And I add to that 37.55 milliliters of 0.223 molar NaOH. What's the concentration of the acid? So it's just like problems we were doing a chapter or two ago. So I have 10.0 milliliters of this, but I don't know the concentration. And I have 37.55 milliliters of this, and it's 0.223 molar. So I want to figure out, okay, I know this concentration of volume. So basically what this is saying is, drawing on the board, so I don't have to hide our slide. I have an Erlenmeyer flask down here, let's say, and it has 10.0 milliliters of the acid. So I actually did a titration, and I added in 0.223 molar NaOH. And I added it. Stayed clear, stayed clear, stayed clear, 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 clear. Boom! Turned pink. When did it turn pink? It turned pink after I added 37.55 milliliters. Oh, okay. So that tells me when it turned pink. So however many moles of base I added, that must have been equal to the moles of acid that were down here. So how many moles of base did I add? Well, we can figure that out. I got the volume of the base times the moles per volume of the base. So let's try this. So 37.55 milliliters of NaOH. And the concentration was 0.223 moles NaOH per liter, or I'm going to use my little shortcut. A liter same as 1,000 milliliters. Oh, well, for every 1 mole of base I added, I must have neutralized 1 mole of acid, right? It's 1 to 1, see? So this should look a lot like every other one we've done. For every 1 mole of NaOH, I must have reacted with 1 mole of acetic acid. So let's see. What does that give me? Grab a calculator here. I got 8.37 times 10 to the third. Is that what you got? Anybody? Okay. Try that again. 8.37 times 10 to the negative third. That's how many moles of the acid I have. Well, I want to know the molarity of the acid. What's molarity? What's the units on molarity?
Moles per liter.
Moles per liter. So I know my moles. Well, what was the volume of the acid? 10 milliliters. So take my moles, divide it by my volume, but in liters. Okay? So I'm going to have to do a little erasing here to make room. I'm going to erase over here, I guess. La 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 la. Okay. So I want molarity, which is moles per liter. Got my moles. What's my liters? Let's turn 10 milliliters into liters. 1 milliliter is 10 to the negative third liters. So 0.0100 liters. So my molarity is moles, 8.37 times 10 to the negative third moles. per liter. 0.0100 liters. Which I think is going to be 0.0837. Something like that. Try it real quick. Nope. 0.837. There we go, sorry. So I knew the one, so I could find the other. Okay, we only got 5 minutes here. So let's try and do one more, and then you can, if we have time, we'll finish up, maybe do a little bit at the beginning of the lab just to wrap it up. But okay, perfect. Okay, so let's do this one real quick. So, say I had the titration of 15 milliliters of hydrocyanic acid requires 26.85 milliliters of 0.100 molar strontium hydroxide. Same thing. What's the concentration of the acid? So I have 15 milliliters of the acid. I add in base until it turns pink. So first we got to write a balanced equation for this because it's not given to us. So hydrocyanic acid plus strontium hydroxide. What's the formula for hydrocyanic acid?
HCl.
Okay, so hydroic tells you it came from what? Ide. So cyanide. Yes, cyanide is Cn negative. So you would need one hydrogen to balance out a Cn negative. So yes, HCN. What's strontium hydroxide's formula? What's strontium's charge?
Plus 2.
2 plus. What's hydroxide's charge? 1 negative, so SR parentheses OH2. Okay, good. Okay, so we're going to react these. So now I'm going to combine hydrogen with hydroxide and strontium with cyanide. So hydrogen and hydroxide, that's just water. And strontium and cyanide, well, strontium's 2 plus, cyanide's 2 negative. I mean 1 negative. You told me, so I need 2 of them. Right. Okay, let's balance this real quick. I'm going to need 2 hydrocyanic acids and 2 waters. It looks like. Okay, let me change colors here. So what do we know? We know 15.0 milliliters of HCN. And I want to find the concentration, the moles per liter. I also know it took 26.85 milliliters of 0.100 molar strontium hydroxide. So this is basically exactly what we were doing. What was that, chapter 8, where we were doing this? We were using molarity and stuff to find the other molarity or find the other volume and stuff. So if I know that molarity, how do I find that molarity? Well, let's start with what we know. So I'm going to take 26.85 milliliters of strontium hydroxide times 0.100 moles strontium hydroxide per liter, or in our case, we can say 1,000 milliliters. But I want to turn strontium hydroxide into hydrocyanic acid. What's the relationship between the two? Now it's not 1 to 1, right? 1 to 2. For every 1 strontium hydroxide, I neutralize 2 HCN, right? See that? So for every 1 mole strontium hydroxide, I neutralize 2 moles HCN. So how many moles of HCN is that? So we are out of time. I'm going to punch it in super quick. 26.85. $5.37. That's a negative third. Is that what you got? What
Yeah,
are-
5.37.
Okay, that's the moles of HCN. What's the molarity? Oh, take those moles divided by the volume. So 5.37 times 10 negative third moles over my volume, which was 15 milliliters. So if I turn that into liters, it's going to be 0.0150 liters. I don't have time to show you that, but you know how to turn milliliters into liters, I think. And 0.358. Point 358 molar. Okay, so here's your mission. Do this one. Do number 11 between now and lab. I will ask you for that one at the beginning of lab. And then we'll finish up the last couple of slides, which is all just theory, no more calculations. So do number 11. We'll do that. We'll do our last lab. So I'll see you on Wednesday.